Welcome to section 3.1. We're going to talk about derivatives of polynomials and exponential functions. So here are some rules to kind of follow. The first one is if I'm taking derivative with respect to x and I have some other variable or number, which is represented by c, that will always result in the derivative of 0. If it's x just to itself, it would always result in the value of 1. And then 3 is any variable to a certain power will always equal n times x to the n minus 1 for any real number. This is called the power rule. This is also why number 2 is true as well. So I have a proof of why that's true. I'm using the definition of derivative to get this. And basically what happens is that when you plug this in, you write a general form, x to the n cancels itself out. And then once you divide all the h's out, you're left with the first term, which is n times x to the n minus 1, which is the only thing left after you plug in 0. So applying this rule to all our simple stuff, we make finding the derivative actually pretty short and sweet. So for the first one, letter A, I have x to the 9th. So that means I'm going to take the power of what I have and move it out front. And then the power that I currently have will become 1 less. So then the result will be 9x to the 8th. Okay? Now it doesn't have to be always x. So for letter B, same thing happens. 13 moves down. 13 for our power becomes 1 less. So I get the derivative of 13t to the 12th. For letter C, we're taking the derivative with respect to r. So then the 11 gets moved down, or out front of our r, and then the 11 becomes 1 less. So we have 11r to the 10th. Now for letter D, we have to rewrite the square root here. So it's the same thing as x to the 1/2 power, because it's a rational exponent. But then I can apply the power rule from there. So the 1/2 moves down. And then it's times x to the negative 1/2. Remember, I'm subtracting 1/2 from 1, or 1 from 1/2, so that's how I get that. Now I can also rewrite this in a different way. So the negative exponent tells me move it down to the denominator, and then a 1/2 power means the square root. So I can say 1 divided by 2 square root of x. For letter E, I have to rewrite this before I can use the power rule, so I have to move x to the 7th up to the numerator to make it x to the negative 7th. But then I can apply the power rule and say negative 7x, and then 1 less than negative 7 is negative 8. So my answer would be negative 7 times x to the negative 8th. I can also rewrite this one by moving the x to the negative 8th down to where it was before, so it would be negative 7 divided by x to the 8th. Letter F is like letter D, where I have to rewrite the radical, so it would be t to the 3/5 power. But then from there I can apply the power rule and move the 3/5 down. 1 less than 3/5 will be negative 2/5. I could leave it like this, or I could rewrite it so the negative 2/5 tells me to move the t down to the denominator where the 5 is. And then I can rewrite the rational exponent into radical form. So I get 3 divided by 5 times t, or the 5th root of t squared. Now I have 3 more kind of differentiation rules for you. If I have a number that's multiplied to a function, I can move that scalar out and take the derivative of the function. 5 and 6 are basically the same thing, where if you're adding or subtracting 2 functions together, you can separate them and individually look at them and take their derivatives by themselves. So example 2 here, we have some more kind of a little bit more extensions of what we're doing. So when I have a constant or a coefficient in front, I'm still going to move the 6 down for the power rule, but it gets multiplied to the coefficient in the front. So that's how I get 24x to the 5th. A letter B, same thing, it happens for all of them. So the 3 gets moved down to multiply to the 3. Now, because it's 4x, it's actually to the first power. So that gets moved down. So x becomes the 0 power. 2 is a constant, so it becomes 0 and goes away. So I get 9x squared minus 4. Remember that x to the 0 is 1, so that cancels itself out as well. So that's why there's no variable there. Letter C, doing the same thing, I'll move the 7 down to multiply to the negative 4. I'll move the 3 down to multiply to the negative 5. And I'll move the 2 down to multiply to the 3. So that gets me negative 28 x to the 6th minus 15x squared plus 6x. Okay, and then letter D, same idea. I'll move the 4 down to multiply to the 5. I'll move the 2 down to multiply to the negative 6. Now 1,000 is a constant, so it becomes 0 and goes away. So my answer will be 20m cubed minus 12m. And that's it. Now I can apply this idea to other things that we've already talked about. So like finding the equation of a tangent line given a function and a point. Now for this one I have to rewrite this function so I can apply the power rule. So the square root of x needs to be rewritten as x to the 1/2. Like bases that are multiplied, I add the exponents, so that's how I get 3/2. And then I can apply the power rule. So that's how I get 3/2 x to the 1/2 plus 1. Now because this is the derivative, I want to find the slope at the point 1, 2. So I need to plug in 1. And that allows me to find that the slope at 1, 2 is 5/2. And once I have that, now I can use the slope-intercept form equation to plug in what I already know. So first, I'll be able to plug in 5/2 in for m. And because I have a point 1, 2, I can plug that in as well to help me find my y-intercept. So 5/2 times 1 is 5/2. I'll subtract 5/2 to both sides. 2 is the same thing as 4/2. So 4/2 minus 5/2 is negative 1/2. And that is my y-intercept. So I'll go back and plug it in. So the tangent line equation that I get is y equals 5/2 x minus 1/2. And that is my answer. Okay, one more differentiation rule here is what happens if I take the derivative of e to the x. So when I plug it into the definition of derivative, what happens is that I'm able to simplify it down to where it's e to the x times the limit of eh minus 1 all divided by h. But if I graph that, as I'm approaching 0, you're actually approaching 1 from both sides. So using that as a result, I can plug that in, and really, the derivative of e to the x is e to the x. And so using that, I'll be able to kind of do some more derivatives when I have e to the x involved. So for our last example, I want to be able to take 3 derivatives of g of x using 1 over x squared minus 3 e to the x. So I have to change 1 divided by x squared to x to the negative 2nd. But then from there, I can take the first derivative. That means I'm going to get negative 2x to the negative 3rd. But because it's e to the x, it just actually stays. So the 3 doesn't move. It's just minus 3 e to the x. The second derivative becomes 6x to the negative 4th because negative 2 times negative 3 is 6. But then minus 3 e to the x stays the same. And then the last derivative will be negative 24x to the negative 5th minus 3 e to the x. So notice that 3 e to the x never changed because the derivative of e to the x is itself. And that's it. Okay, thanks for watching.